Hello, hello. This is QMG, and I have a nice video to criticize. It's a very famous video in the internet, and it explains the double slit experiment, which is a very famous experiment in quantum mechanics. And well, I would like to show you the video because it attempts to explain the physics, but I'm gonna make a lot of criticisms about this one, I think. So let's take a look at it.
The infamous double slit experiment. To understand this experiment.
By the way, I love the animation in this video. Okay, they did a wonderful job doing that. It's a wonderful cartoon for kids.
We first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right.
Well, so far nothing strange is happening here. You know, common sense information, and of course they're going to go over wave mechanics as well, and then they're going to try to combine them together.
Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly.
Right. So, right, you obtain a diffraction pattern, which kind of looks like that, more or less. Okay, so it's not completely accurate. Okay. Oh, wow, somebody's calling me.
In line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make.
Similar, but not exactly the same way. You can actually detect. My goodness, look at this! Somebody call me. Wow. Yeah, you can actually see a wave pattern in that diffraction pattern. So you can actually see that it's a wave, but more or less is accurate what he's saying.
When we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall.
And by the way, this was known a long time ago. In fact, Newton used to believe that light was composed of little particles that were projected at great speed. And there was a guy who actually noticed an interference pattern with light, playing with slits, kind of like the way he's showing right now. And, he started questioning, well, is it really particles coming out of it? Because, it looks more like a little wave pattern that you observe. So this is sort of important. This interference pattern is what indicates that you actually have a wave.
Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
Right. So there are places where you have where it's most likely to happen, right? Those are the bright lines, and there are places where it's very unlikely to make a detection of a wave, which is in the dark places. That's how you can interpret that. You can interpret that in terms of probability. So let's continue.
So, when we throw things, that is, matter, through two slits, we get this.
Okay.
Two bands of hits.
Sure,
and with waves, we get an interference pattern of many bands.
Okay, great.
Good so far. Now,
so good.
Let's go quantum.
Okay. This is where it's going to get very interesting. And let's pay very close attention to the assumptions that are made, because I saw this video before, and they make the way they make assumptions at the beginning is how they make a particular interpretation later on.
An electron is a tiny, tiny bit of matter.
Okay, so they're starting with electrons as being tiny, tiny pieces of matter. Okay, so if you know the debate in quantum mechanics is particle versus waves, and somehow he's like, no, these are particles. Okay, so he's assuming, okay, we are starting with particles.
Like a tiny marble.
Marble.
Let's fire a stream through one slit. It behaves just like the marble, a single band.
Sure.
So,
kind of like a band because it's a little more distributed. So I think the cartoon got it very accurately, but they just, in order not to distract you, they just move it very quickly. But let's
shoot
continue.
these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference?
Yeah, okay, so yeah, if you start with particles and then you start showing an interference pattern, then you're confused, right? Kind of like the example I gave of Newton, right? Newton thought it was particles, so if you start observing an interference pattern, then you're puzzled about it, right? But you could also assume that these electrons are in fact waves all the time, so they are not really at any moment particles, like localized in one place, but they're kind of waves, one wave, two waves, three waves. So those electrons, so the waves are actually quantized in some ways, but they are not particles, they are waves, right? So let's continue watching this one. So if you start with the assumption of particles, of course you're gonna get puzzled, just the way he showed right now.
Pattern. We fired electrons, tiny bits of matter. We get a pattern like waves, not like little marbles.
Well, yeah, because you're saying they are particles, right? So if you assume you're shooting a bunch of waves and you get a wave pattern, well, there's nothing confusing about it. So as you can see, they're picking a very particular interpretation.
How could pieces of matter create an interference pattern like a wave?
Because they were waves?
It doesn't make sense.
Yeah, it doesn't make sense to you.
Physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern.
Okay, so again, I don't think at any moment anybody thought that they were just particles. Maybe they conceive them as wave packets, right? And he says bouncing off each other. I think a better way to say that is, it's like at some point maybe they thought that the reason you get a wave pattern was that it's kind of like when you produce sound waves, right? When you produce sound waves, basically what you have is compressions and decompressions everywhere of all the molecules that form the air. So they were kind of thinking like that about the particles, and maybe they're kind of compressing and decompressing in some ways, or maybe shaking up and down, or some kind of wave as a collection. But if you remove everything else and just leave one alone, then you don't have a wave, right? Kind of like if I try to produce sound with just one atom, right? It will not be possible. I can shoot it, but I cannot produce a wave because I need all the collection of particles around me to start producing compressions and decompressions, which is what sound waves are.
So they decide to shoot electrons through one at a time.
Yeah. This is my point. Maybe when they were shooting electrons one at a time, maybe they were not really shooting electrons one at a time. They were shooting wave packets one at a time.
No way they could interfere with each other. But after an hour of this, the same interference pattern is seen.
Of course, if you're shooting waves one by one, you're gonna get another interference pattern, right?
Birds. The conclusion is inescapable. The single electron leaves as a particle,
Okay.
becomes a wave of potential,
Notice the fantastic
decide to shoot
explanation they give.
electrons through one at a time. There is no way they can interfere with each other.
Yeah, there's no way us particles interfere with one another, but you keep assuming that.
But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable.
Okay, so here's the conclusion. Okay, instead of starting with wave packets, they insist with particles. Notice the explanation they give for the interference pattern. And he said it's inescapable. Somehow there's no other way of explaining it.
The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes.
Goes as a wave of potential. So the particle comes out a wave of potentials. I don't even know what he means by that.
With itself to hit the wall like a particle
before hitting the wall. Isn't it easier? Oh wow, look at this, my phone. Isn't it easier to assume that you had a wave packet to start with? Hit the slit, the two slits, and then create an interference pattern, right? I mean, that's a more simple explanation. On the other hand, even in this interpretation that the electrons come out as waves already, of course, there are some points, some subtleties to deal with, right? Because once it hits the screen, you detect just one bump. Okay, so it's almost like you collapse the whole thing at one point, right? It's kind of like you burst a bubble, right? The whole thing is expanded everywhere. Once you make the detection here, the whole thing, explodes. It's almost like that little tiny place is connected with the other one. So there's also something spooky about the interpretation of wave packets. Okay, going into the two slits. Okay, but it's not the only explanation, the one that they are offering. Okay, that one is weird. Mine is weird, and of course there are more weird explanations, more weird ways of interpreting what you are observing right here.
Mathematically, it's even stranger. It goes through both slits and it goes through neither.
Now they go into the mathematics, and it says it goes through one or it goes through neither. I even don't think they got the mathematical description. The accurate mathematical description is it goes through one, it goes through the other, or it can go into one and transform into the other, or it can go into the other and transform into the other one. Okay, so it's more complicated like that. But the point here is about physical interpretation for that, right? There are many ways to interpret it, and there's not just the way they're trying to interpret the whole thing.
And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they just...
Yeah, I'm sure they were baffled. I agree with that. Especially when you try to find an explanation for that. As you can see, there are many ways to look at it, not just the way they're looking at the information.
Decided to peek and see which slit actually goes through. They put a measuring device by one slit to see.
Okay, I'm gonna criticize here the cartoon. Okay, notice they put an eye. Okay, the mesh when you try to determine what slit the electron went through, it's not like an eye. It's like you're looking at something. It's more like you're interacting with it. You're actually changing it a little bit. You're interacting with it and trying to leave it exactly the same way. But the thing is, when you make a measurement, you sort of affect the behavior of the thing that you're kind of measuring. Try to leave it exactly the same way, but you don't in this case. Okay, let's continue watching.
Which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined.
Okay.
When they observed, the electron went back to behaving like a little marble. It produced...
Okay, so they were saying when you actually try to observe which slit it goes through, it behaves just like a little marble. In other words, you lose the interference pattern. And that can also be explained with the waves. Okay, so you start with a wave, and it goes through the slits. Okay, so wave can be expanded, go through the slits. When you actually observe the wave in one of the slits, basically what you're doing is if you have a wave, right? If you have a wave, and basically you're playing with the phase shift. You're shifting the wave in random ways. Okay, so when the wave from one slit arrives to the screen, it doesn't interfere with the wave coming out of the other slit, because now you sort of shifted the wave. Okay, so that's one wave explanation of why you recover the the particle behavior after you do an observation, which is not really an observation, it's an interaction.
It's a pattern of two bands, not an interference pattern of many.
Right.
The very act of measuring or observing which slit it went through meant it only went through one.
Right, because you are playing with you're shifting the wave, okay, in random ways when you are observing it. It's kind of like if you put a bunch of detectors around a slit, it kind of like it makes the wave sort of change a little bit in random ways, and so you no longer have constructive and destructive interference on the screen.
Not both. The electron decided to act differently.
By the way, that wave explanation, you can find it in this book right here. Okay, this is Quantum Mechanics by David Bohm. I don't show you the front because it's gone, but there's it's a nice chapter that explains that. So yeah, you can explain that with waves. You don't have to use their particular interpretation.
As though it was aware it was being watched.
Okay, now they go into the quixotic thing, okay? As if the electron knows it was being watched. No, you interacted with it.
And it was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves?
Yeah, well, you can stick to waves so far, except that you get some spooky connection between events, but I find it more simple to think in terms just of waves instead of switching back and forth in terms of particles. But hey, any interpretation of the experiment, I say is valid. Okay, whatever works for you.
And waves of what? And what does an observer have to do with it?
And that's a good question. Waves of what, right? What is that thing vibrating, right? If as I said, if a wave packet comes out, I mean, it's a wave packet of what? What is it that is really shaking in their space? Who knows, right?
This. The observer collapsed the wave function simply by observing.
Not by observing, by interacting with it, and that's what we call observation. All right, well, that's the double slit experiment. Okay, everyone has to be familiarized with it. As you can see, there are many ways to interpret it. Okay, now that's one particular interpretation. There's also the Bohm interpretation. Okay, you can assume the particles follow trajectories and there's a force moving it around. Well, whatever you choose. All right, bye-bye.